If you look at the famous King's Chamber, its walls and its roof, the ceiling of the King's Chamber are all made with gigantic granite blocks.
For 40 years, Graham Hancock kept pointing to the same piece of ancient stone and asking a question the academic world struggled to answer. He was dismissed as unqualified. His ideas were called dangerous. His work was accused of challenging the accepted story of human history. But then something changed. A material scientist examined 4,000-year-old Egyptian granite under a scanning electron microscope, and what appeared inside the ancient cutting grooves was not what conventional methods would predict. It wasn't simply sand, it wasn't copper residue, it was a mineral with a hardness of 9 on the Mohs scale, the kind of material used today to cut some of the hardest engineering materials on Earth. And the most disturbing part? That mineral had been embedded in those ancient grooves for thousands of years. Suddenly, the question Hancock had been asking for decades looked very different. So, how did ancient Egyptian craftsmen cut, drill, and polish granite with such precision? And what does the evidence actually tell us? Before we uncover the mystery hidden inside these ancient stones, make sure you subscribe to the channel and turn on notifications, because what we're about to examine could challenge everything you thought you knew about ancient Egyptian technology. The real mystery may be hidden inside the stone itself. Ancient Egypt relied heavily on 2 major building materials: limestone for much of its massive construction, and granite for the structures and objects that had to endure. Granite appeared wherever permanence mattered most: the casing and internal sections of monumental structures, the passages and chambers of the Great Pyramid, enormous obelisks, royal sarcophagi, and the sacred inner spaces of major temples. When the Egyptians wanted something to survive for generations, they often turned to granite. Much of this granite came from the quarries at Aswan, roughly 900 kilometers south of Giza. From there, enormous blocks were transported north, most likely along the Nile, toward the great construction centers of ancient Egypt. Inside the Great Pyramid, the King's Chamber is constructed from Aswan granite. Above it are 5 layers of enormous granite beams forming the relieving chambers. Some of these slabs weigh between 25 and 70 tons, yet they were shaped, positioned, and fitted with remarkable precision. Then there is the granite sarcophagus inside the King's Chamber. It was carved from a single block of red granite, and its dimensions are so large that it could not simply have been carried through the pyramid's present entrance. This suggests that it was positioned inside the structure during construction, before the surrounding passages and chambers were completed. But even the Great Pyramid may not represent the most remarkable granite work left behind by the ancient Egyptians. For that, we have to travel to the Serapeum at Saqqara. Beneath the desert south of Cairo lies a vast underground complex carved directly into the bedrock. The Serapeum was associated with the sacred Apis bulls, and within its enormous chambers are massive granite sarcophagi, monumental stone boxes carved from single blocks of red and black granite. Some of these containers weigh between 70 and 80 tons. Their lids alone can weigh around 27 tons. And when you examine the workmanship, the scale becomes only part of the mystery. The surfaces were carefully finished, and the enormous lids were designed to meet their corresponding boxes with remarkable precision. Some researchers have argued that the level of contact would have required extremely tight tolerances across surfaces several meters long. The stone doesn't simply look massive. In places, it looks engineered. The exterior surfaces of several granite boxes are remarkably smooth and highly polished, producing a finish capable of reflecting light across the chamber walls. That raises an obvious question. How exactly was this level of finish produced? The conventional explanation generally points toward stoneworking techniques involving softer tools, abrasives, and repeated grinding and polishing. But critics of that explanation argue that certain examples of Egyptian granite workmanship appear difficult to reconcile with the capabilities normally attributed to those methods. And this debate is not new. More than a century ago, one of the earliest systematic investigators of Egyptian archaeology encountered evidence that he found difficult to explain. His name was Flinders Petrie. During his work in Egypt in the late 19th century, Petrie examined hollow cylindrical cores made from Aswan granite. Some of these cores contained distinctive spiral markings running along their surfaces. Petrie studied those grooves closely. He estimated that the cutting process appeared to advance roughly 0.1 inch with every revolution of the tool. In other words, every complete rotation appeared to push the cutting action approximately 1/10 of an inch farther into the granite. For Petrie, this was not an insignificant observation. He considered the cutting performance extraordinary and believed the evidence pointed toward a process far more effective than the methods commonly attributed to ancient Egyptian craftsmen. And remember when this was happening: the 1880s. Petrie's observations eventually became part of the archaeological literature, but the larger question remained largely untouched. If the ancient Egyptians were using the simple tools traditionally described in textbooks, how were they producing some of these remarkably precise results in one of the hardest stones they had access to? That question would eventually attract the attention of Graham Hancock. Hancock, born in Edinburgh, Scotland in 1950, did not begin his career as an Egyptologist. He worked as a journalist, including for The Economist and other major publications. His approach was shaped by journalism. Don't simply accept a claim, ask for the evidence behind it. When Hancock applied that mindset to ancient history, particularly to ancient Egyptian construction, he began questioning whether the conventional explanations actually demonstrated what they claimed. His arguments were not limited to vague stories about mysterious lost civilizations. He focused on specific evidence: precision stonework, unusual machining marks, massive granite structures, and ancient objects whose manufacture he believed deserved a much closer technical examination. In 1995, Hancock published Fingerprints of the Gods, which went on to sell millions of copies and turned him into one of the most recognizable alternative history writers in the world. His arguments generated intense controversy. Supporters saw him as someone willing to challenge assumptions that had become accepted simply because they had been repeated for generations. Critics argued that his interpretations went far beyond what the archaeological evidence could actually establish. The conflict became about more than granite. It became a battle over how we interpret the ancient past. Hancock continued asking whether certain technological achievements had been fully explained, while professional Egyptologists largely rejected his broader conclusions. One major criticism was straightforward. Hancock did not have formal academic credentials in Egyptology. But that created another question. Should an argument be rejected because of who made it, or should the evidence itself determine whether the argument survives? For decades, the debate continued. Hancock kept returning to the same underlying problem. If the accepted tools can explain the ancient granite work, then demonstrate exactly how. Show the process, reproduce the results, measure the cuts, explain the marks. And if the conventional methods cannot reproduce what we actually find in the stone, then perhaps the question isn't whether Hancock was right about every part of his theory. Perhaps the more important question is whether we have been asking the wrong question all along. Then, in 2022, Hancock's ideas reached an audience far beyond archaeology when Netflix released his documentary series. The debate that had once been confined largely to books, academic arguments, and archaeological circles suddenly entered millions of homes. But the granite itself remained unchanged. The grooves were still there. The cores were still there. The enormous stone boxes were still there. And the question that had been raised more than a century earlier was still waiting for a definitive answer. What technology did the ancient Egyptians actually use to shape granite with such extraordinary precision? Ancient Apocalypse took Hancock's arguments to an audience of millions, turning a long-running archaeological controversy into a mainstream conversation almost overnight. The response from the archaeological establishment was immediate. The Society for American Archaeology issued an open letter to Netflix, criticizing the series and arguing that it presented pseudoscientific claims that could distort the public's understanding of the ancient past. Then, in 2024, Hancock faced archaeologist Dr. Flint Dibble in a widely watched discussion on the Joe Rogan Experience. More than 10 million people reportedly watched the exchange. The conversation was intense, detailed, and surprisingly revealing. Not necessarily because one side defeated the other, but because it exposed something much more important. After decades of argument, the central technical question surrounding ancient Egyptian granite was still unresolved. Hancock's challenge had always been remarkably simple. If ancient Egyptians really produced this work using copper tools and abrasive sand, then demonstrate it. Recreate the process. Use copper. Use the appropriate abrasive. Produce the same cuts, the same grooves, the same surfaces, and the same precision found on the ancient artifacts. That demonstration had not been convincingly achieved, and that is where the investigation took an entirely different direction. Instead of debating what the Egyptians should have been able to do, someone decided to examine the ancient cuts themselves. But before we get to what the microscope revealed, we need to understand what conventional archaeology would expect to find, because the expected evidence is just as important as the unexpected evidence. Copper has a Mohs hardness of roughly 2.5 to 3. Granite, meanwhile, contains several minerals, including quartz, feldspar, and mica. Quartz is particularly important here because it has a hardness of around 7. The basic principle behind abrasive cutting is straightforward. The cutting material needs to be harder than the material being removed. Otherwise, instead of cutting the stone efficiently, the tool itself deforms and wears away. So how could relatively soft copper be used to work extremely hard granite? The traditional answer is abrasive sand. Quartz-rich sand could theoretically sit between a copper tool and the granite surface. The copper would provide the pressure while the harder sand particles performed much of the actual abrasion. On paper, the idea appears plausible. But there is a problem. The copper itself deforms under heavy pressure. As that happens, abrasive particles can become trapped inside the softer metal. The cutting efficiency then changes, and the tool begins wearing down rapidly. This is where experimental archaeology becomes important. Dennis Starks, an experimental archaeologist associated with the University of Manchester, spent years attempting to reproduce ancient Egyptian stoneworking techniques. He constructed replicas of copper tube drills and flat copper saws based on the tools traditionally attributed to the Egyptians. He also used appropriate abrasive material and attempted to follow the proposed ancient process as closely as possible. The experiments demonstrated something important. Yes, copper combined with quartz sand can eventually cut granite, but the process is extremely slow. The rate of penetration can be measured in millimeters per hour, while the copper tool experiences significant wear and requires frequent replacement. And the resulting surfaces are another problem. They tend to be rough and irregular rather than resembling the remarkably continuous spiral grooves documented in ancient granite cores. That distinction matters, because the question isn't simply whether copper and sand can eventually remove granite. The real question is whether they can produce the specific evidence we see in the ancient stone. And even Flinders Petrie had reservations about the conventional explanation. When Petrie examined ancient drill cores in the 19th century, he argued that the efficiency suggested by the spiral grooves pointed toward something more sophisticated than a simple copper and sand arrangement. He proposed that the cutting mechanism may have involved fixed cutting points made from a material harder than quartz. Among the possibilities he considered were corundum and gemstones. Remember when Petrie made that observation? The 1880s, more than a century before modern scanning equipment could examine those ancient surfaces at microscopic scales. Yet over time, the copper and abrasive explanation became the standard framework, while Petrie's concerns received far less attention. Then another perspective entered the debate. Chris Dunn, a precision machining professional with decades of experience working with CNC machinery and aerospace-level tolerances, personally examined ancient Egyptian stonework. His observations were striking. He reported extremely flat surfaces extending across large areas, drill holes maintaining remarkable circularity through their depth, and machining characteristics that he believed resembled the precision achievable through modern manufacturing. From an engineer's perspective, these were not simply crude ancient surfaces. They displayed characteristics that demanded a much closer technical investigation. And this created a fascinating situation. Experimental archaeology was struggling to reproduce the ancient results using copper and sand. Meanwhile, professional machinists were identifying features that appeared unusually precise. At that point, the most reasonable next step wasn't another argument. It was an examination of the evidence inside the stone itself. If the ancient cutting process had left microscopic traces, perhaps those traces could reveal what actually performed the cutting. That was the question Dr. Masudi wanted to investigate, and this is where the story takes a dramatic turn. Dr. Masudi specializes in tribology, the scientific study of friction, wear, lubrication, and what happens when two surfaces interact under pressure and motion. It's an extraordinarily precise field of materials science. Tribologists study the microscopic evidence left behind when materials slide, grind, scrape, or press against one another. Their work can reveal not only that a surface was damaged, but sometimes how that damage occurred. And that made Masudi's expertise particularly relevant. He wasn't an Egyptologist defending an established theory. He wasn't an ancient history writer trying to prove a controversial idea. His field was materials, friction, wear, microscopic interactions between surfaces. And now, for the first time, that scientific perspective was being directed at the ancient granite itself. The question was no longer simply, what tools do historians think the Egyptians used? The question had become far more direct. What does the stone itself say? And when the scanning electron microscope finally went in for a closer look, the answer was not what the conventional model had predicted. That independence mattered. For this investigation, Dr. Masudi was not approaching the evidence as an Egyptologist trying to defend an established interpretation. His expertise was in materials science, which made his perspective especially valuable. The investigation relied on two powerful analytical techniques. The first was scanning electron microscopy, or SEM. Unlike an ordinary optical microscope, an SEM can examine surfaces at magnifications thousands of times greater, revealing microscopic structures invisible to the naked eye. The second was energy dispersive X-ray spectroscopy, commonly known as EDS or EDX. This technique goes beyond simply producing an image. When the sample is bombarded with electrons, it emits characteristic X-rays. By analyzing those X-rays, scientists can determine which chemical elements are present in the material. Together, these methods can answer two very different questions. What does the surface look like? And more importantly, what is actually inside it? Masudi and his team applied these techniques to ancient Egyptian granite, examining the interiors of cutting grooves created roughly 4,000 years ago. These surfaces had remained preserved for thousands of years, and now, for the first time, they were being examined at a microscopic level that earlier researchers simply did not have access to. The expectation was straightforward. If the conventional explanation was correct, the microscopic evidence should reveal traces consistent with quartz, sand, and copper, the materials traditionally proposed for cutting granite. Instead, the analysis produced a result that demanded attention. The researchers detected corundum, aluminum oxide, or Al2O3. Corundum is the mineral that, in its crystalline forms, gives us gemstones such as rubies and sapphires, and its hardness is remarkable. On the Mohs scale, corundum ranks at 9. Quartz is only around 7. That means corundum is significantly harder than the quartz contained within granite and harder than the other major minerals making up the stone. Only diamond ranks higher on the standard Mohs hardness scale. That is precisely why corundum is so valuable as an abrasive today. Industrial manufacturers use it when extremely hard materials need to be ground, polished, or cut. But the most important detail wasn't simply that corundum was detected, it was where it was found. The particles were located within the ancient cutting grooves themselves. Their distribution and concentration were consistent with the material being involved during the cutting process, rather than simply appearing on the surface later through accidental contamination. In other words, the microscopic evidence appeared to point toward corundum being present while the granite was actually being worked. But the microscope revealed something else that made the result even more intriguing. When stone is cut through uncontrolled hammering or inconsistent abrasive action, the damage doesn't necessarily stop at the visible surface. Tiny fractures can develop beneath the cut. These microcracks spread downward and outward from the cutting line into the surrounding stone. Different cutting processes leave different microscopic signatures, and experiments involving copper and abrasive sand can produce this kind of subsurface damage. But the ancient surfaces examined in the investigation appeared different. Instead of widespread subsurface fracturing, the researchers reported a comparatively clean boundary between the cut surface and the untouched granite. That suggested something about the way force had been applied. The cutting action appeared controlled, directional, consistent. Rather than energy being randomly dispersed into the surrounding stone, the force seemed to remain concentrated along the cutting path. From a tribological perspective, that pattern is more consistent with a hard abrasive being moved along a controlled trajectory under relatively stable pressure, and that is very different from a softer copper tool carrying loose sand particles across granite. But there was another problem. Where would the ancient Egyptians have obtained corundum? Corundum is not found throughout Egypt in deposits that would obviously provide an abundant source of high-quality abrasive material. Major natural sources existed elsewhere, including regions of India, Sri Lanka, and parts of the eastern Mediterranean. That doesn't necessarily make ancient Egyptian access impossible. Quite the opposite. Egypt was connected to one of the most extensive trade networks of the ancient world, and there is archaeological evidence that naturally occurring abrasive materials containing corundum were known and traded in the ancient Mediterranean. One particularly important material was emery, a naturally occurring mixture containing corundum. Historical sources indicate that emery from the Greek island of Naxos was being used by craftsmen across the Aegean world from at least the Bronze Age onward. So the possibility existed. Ancient craftsmen could potentially obtain corundum-bearing materials through long-distance trade. But that raises an even bigger question. If they were deliberately obtaining and using these materials, then we are no longer talking about a simple copper tool dragging ordinary sand across granite. We are talking about a specialized abrasive technology, a technology that would require selecting the right material, acquiring it, incorporating it into the cutting process, and controlling how it interacted with the tool and the stone. And that is exactly where the debate becomes interesting. Because finding evidence of what was present is only half the problem. It doesn't automatically prove that the proposed technique could actually produce the extraordinary results found on ancient granite. Hancock understood that distinction. He knew his critics could make the obvious argument. Fine, maybe corundum was present, but can it actually explain the cutting? There was only one serious way to answer that: test it. So the investigation moved from the microscope to the workshop. In early 2023, Hancock arranged controlled cutting experiments in an operating granite workshop. The setup was designed to compare different abrasive conditions under controlled circumstances. Granite blocks were prepared. Copper tools were used. Different abrasive materials were tested separately. Experienced granite craftsmen worked alongside materials specialists, while the cutting process was measured and documented. The first trial attempted to reproduce the conventional explanation as closely as possible. Copper tools, ordinary sand, granite. The result was familiar. The cutting rate was extremely slow, around 0.5 millimeter of progress per hour. The copper deteriorated rapidly, and the resulting surfaces were rough and irregular. They looked nothing like the smooth, continuous characteristics observed on some ancient granite examples. The traditional method had produced exactly the kind of result that previous experimental work had suggested. It could cut the granite, but it struggled to explain the precision. The second experiment changed the abrasive. Instead of ordinary sand, the researchers used finely ground quartz powder. The particles were smaller and more consistent, but chemically they were still essentially the same material. The performance improved slightly, but not dramatically. The cutting process remained slow, still progressing only fractions of a millimeter per hour, while the resulting surface remained relatively rough. Then came the third test. This time, the copper tool was combined with a slurry containing corundum, with quartz serving as a carrier medium. And almost immediately, the behavior changed. The copper was no longer struggling against the granite in the same way. Instead, it acted as a means of directing the much harder abrasive across the stone. The resistance dropped, the cutting became smoother, and the rate of material removal increased dramatically.